clean. Okay, cool. So it's probability. So since some of you guys don't know what probability is, I will go a little bit detail into this definition here. So first, probability is definitely very important. It's like the greatest of all obstacles if you for scientific research if you don't know probability actually. So what is a probability? Suppose you flip a coin and assume it's a fair coin. So you should expect to have a equal chance to come out with heads or tails, right? And then suppose you flip the coin 10 times. So you can expect that it might come up heads 5 of 10 times, but not necessarily, right? It can also come up like 6 times or 7 times or even 10 times, right? But if you come up with 10 times, you might think maybe this coin is not really fair, but that's another story. So the probability is a mathematical study of random process, such as this flipping coin. Right? It can be used to answer questions like how likely it is to have a coin come up with all 10 heads when you flip like 10 times, right? Or it can answer how likely is that 2 people out of a 50 group out of a group of 50 people have the same birthday, right? So let's continue to focus on this flip coin example. So suppose we have n trials of random process like flipping coin, and small n is the number of times a particular event occurs, like the coin coming up heads. Right. So in this way, the probability of flipping coming up with heads is defined to be like this. So n is the number of times this event happens, and big N is the capitalized N is the total number of trials. So when we do large enough number of trials, then we can get the probability by this formula. And also note that small n, this n is always smaller or equal to big N, so the probability is always between 0 and 1. Okay. So for the flip of fair coin, the probability of head and tail are both 0.5 because they have an equal chance, right? And also you can notice that this pH plus pt this p head plus p tail is 1, right? So so if we want to consider the probability of coming up all 10 tails or 10 heads, this will need another definition for independent events. So what is an independent events? Independent events is the occurrence of one of them in no way influence the occurrence of others. So that means they doesn't affect each other. Let's say, so in mathematics or probability, we believe like when you flip the coins twice, the result of the second time doesn't depend on the result from the first time. So that's kind of independent. Okay. So there is a rule for independent events. So here, so if P1 to PR are the probabilities of our independent events, then the probability of them all happening is by multiply them together. Right, just take a moment to to think about this. Right. So for our example, when we flip the coin, the probability that the first flip will come up heads is, we already know that it's half, right? And the probability that the second will come up heads is also half. And so on and so forth. For the tens, it's still half, right? So in that case, the probability that all 10 flips will come up heads is by multiply these 10 halves together, which is the 0.5 power of 10, right? Which is this is a small number. That means like getting 10 all heads is a rare event, but it's not impossible. Okay, so yeah, here we introduce. Let me see. We do some experiment in Matlab. Here. Right. So in Matlab there is a function called rand. So every time we call it, it will give us a random number between 0 and 1, right? So if you type rand once, you get something like this. If you do it twice, then you get a different number. But they are always between 0 and 1. So actually, you can also do r equals random 10,000, say 1. Right, so in this case, we can look at the size of R. It's 10,000, right? So it's a 10,000 random variables at the same time, and then we plot the histogram of this. So this is a histogram of R. So anyone can tell me what this means? I'll give you guys 1 minute to think about this. And if you know the answer, feel free to unmute yourself, or you can type in the chat window. The distribution of values in the random vector. Correct. Yeah, that's very nice. So yes, histogram is trying to mimic the distribution. Okay, Jacob, that's good for you. You know distribution. That's very cool. Yeah. So histogram is actually counting the number of occurrences during this interval, because all of the possible values are between 0 and 1, right? So then for this bar, that means like over those 10,000 cases, there are like around let's say 900 or over 900 cases falls into this interval, right? Right. So one interesting thing here is although this curve or this shape is not very regular, but you can see the trend that they're almost the same, right? Like each of the bar, I mean the height of each bar is more or less 1,000. Do you guys know why? Yes. Right. So because on average there should be 1,000, around 1,000. So we only put this as 10,000. If we make it larger, that will be more even, actually. Yeah, correct. Good. So let's move on. Right, this we already have this, and let's think about another thing. So now we know. Now we should know independence, right? So when things are or events are independent, then the probability of all the events happening could be calculated by multiplying each of the probabilities. Another rule, so that's rule 1, and there's a rule 2. So rule 2, we need something called, where's that? Mutually exclusive. So mutually exclusive means for each of the experimental trial, only one of them, the result can happen in a given trial. And let's think about this one. So let's think about the question to, so if we want to understand how likely it is for a coin to come up heads 6 times out of 10 times. 6 out of 10 times you flip it. This is essential. So now we wanna know how likely when we flip 10 times we got 6 tails, 6 heads. Sorry. Right, this is more interesting. So here it's like if you want to get 6 heads, then we must have 4 tails, right? And we have to have exactly 4 tails. But so for this case, it's like for the first 6, they are all heads, and for the rest, it's for the last 4, it's tails. But it can also be like this, right? Or it can be like something like this. So we don't care the order. We only care. We only want 6 out of 10 times our heads, right? So if we wanna answer this question, then we need something. So each of this, we need to understand this mutually exclusive, right? So for every time, you cannot make both of them happening. So every case or every trial, you can only make one of them happen, right? So that's called mutually exclusive. And there is a rule for mutually exclusive. So say P1 to PR are separate probabilities of our mutually exclusive events. Then the probability that at least one of them occur is this. We can directly add them together because they are mutually exclusive, which means they don't have overlaps. Every time you can only happen one of them. Okay, so here, like we said, if you wanna calculate 6 out of 10 times, then actually there are many possibilities like this. So you can do this, you can do this, and you can do this. And then the total probability is actually by adding to add them together by using this rule, right? So and then let's think about this. What is this? What's the value for this? That means like for the first tail, for the first trials, they are all heads, and for the rest, it's all tails, right? Because we already know that for the first flip come up with heads is half, and the second is also half, the third is half, and so all of them are actually half, right? So for each of this P, this P, this P, and this P, they are all half to the power of 10. We already mentioned using this independence rule, right? Okay, cool. So we know that each of them are half to the power of 10. And then we have to understand, so we to get the probability that the coin will have 6 out of 10 times, we need to know how many combinations, like how many of those events do we have in total, right? So that is this combination, or we call choose 10 out of 6. And there is a function in Matlab, I think it's called and choose k. So if you choose 1 from 5, then you can have five events or 5 cases. If you want to choose 3, 5, choose 3, and you will have like 10 cases. And for the details of how this n choose k works, there is an appendix here. So I wouldn't go into too much detail for this. But basically, you can this function and the formula to calculate this n choose k is like n factorial of n divided by this. And Matlab has a built-in function for you guys to use. So that's very convenient. Okay. And so far, any questions? Okay, so it seems no questions, so we can move on. After introducing the concept of probability and this independent and exclusive, mutually exclusive, we can think about more examples. Right. So here, let me show the code to you guys. Oh, sorry. This one. So I hope you guys can see this. So I have a function here. Okay. So I have a function called coin flip 1000. And let me do this. Let me give you guys like 2 minutes to read this code. Okay, so because in reality, it's very important to have the ability to read others' code, right? You cannot finish everything by yourself. Like most of the cases, most of the time, you first read and understand others' code, and then make your own contribution. So let me leave you guys 2 minutes to read this code and think about. We don't write directly. That's you can forget about this part. You just focus on the black uncommon parts, uncommented parts. So and try to think about what this function is doing. Yeah, and also if you wanna describe to us, you can directly unmute yourself or type into the chat window. One more minute. Why does it count? Tell us. Oh, I'm not sure what you're asking.
Can you hear me?
Yeah.
So basically where it says if the random number generator produces a 0, it increments
Yes.
the value of heads.
Right.
And then at the very bottom, it says the probability of heads is the number of times that the RNG produced heads, and
Yes.
then you divide that by 1,000. But
Right.
why do you count tails like in your else statement if you don't do anything with it?
Oh, okay. I see what you're saying. Okay. Yeah, you're right. So actually, for if we only wanna, uh, if we wanna only want the final result like this, we don't need tails. The reason I have a tails is for plotting. I will introduce that later. But yeah, you're right. So if we only want this guy, then we don't need this one. Is that your question?
Yeah, thank you.
Oh, okay, no problem. Okay, cool. So I think so let's go through this. So first we clear and close all. Close is close all figures and clear all. So heads is 0. We will first initialize two variables called heads and tails, and we do number of trials to be 1,000. So here we are doing something called Monte Carlo search. So, okay, so since some of you don't know what Monte Carlo search is, let Monte Carlo method. So let's Google it, right? So Monte Carlo method or Monte Carlo experiments are a broad class of computational algorithms that rely on repeated random sampling. So that's the key. Or like different number of trials of random sampling, right? To obtain some probability or something. So for our case here, this is the trials we do. And as you can see, we use a random sample here, right? So this is called Monte Carlo simulation or Monte Carlo experiments. And I believe you guys need this knowledge if you want to finish the homeworks. So, but the idea is simple. So here, we have 1,000 trials, and each time we draw a number from using this function, right? So we can run this guy. So if we do this, so the first time is 1, a 0. Sometimes it's 1, sometimes it's 0, right? But the output is always 0 or 1. So it's a random integer. And then if the result is 0, so 0 represents a head here. So if we encounter a 0, then we add it to the heads, right? Otherwise, it's a tail. And after that, we calculate the probability by dividing the heads by this total number of trials, right? So let's run this code. So we got something around 0.5, right? That's our expectation. Let me uncomment this part. Okay. Then run it again. So this is a graph or a visualization for this, what this Monte Carlo search is doing, right? So let me make it bigger. Oh, wait. Oh, okay. So it can only be this big. Okay, cool. So the title is number of games played. So because this is dynamic, right? So every time you flip the coin, it's either heads or tails. Actually, those two plots are representing the same thing. This is a bar plot and this is a pie plot. And you can see, because we did this for 1,000 times, right? So this is 200 something. And we recorded so here we use tails, right? So for Jacob, the reason I recorded tails is because I want to draw this here. And of course, you can get this by, like, if you do number of trials minus heads, it's the same. So for here, like you said, so if you remember, like previously, they are quite the height of the bar are quite uneven, right? But as the number goes larger and larger, and also for this pie plot, as the number get larger, the percentage will converge to 50% for both of them. Okay, so I hope this example is interesting to you guys. Any questions? Okay, cool. So let's move on. All right, so we have this one. Okay, so before we do that, let me share this code to you guys. Okay, so you guys can copy this to your Matlab. I think copy link. So you guys can enter this link. So the function of coin flip 1000 is I copied it into here, and you can copy this to your Matlab and check the how the function works. Okay, because we will use this function in the following example. Okay, so now we know what coin flip 1000 is doing. Oh, before that, let me. Okay, so here we have another coin flip histogram. Yeah, so let me give you guys 2 minutes to think about what this function is doing. So we call this function. We call the function we just mentioned. So basically, I'm asking what is x? Anyone? Okay, let me explain this part. So for this function, we first create a zero matrix. The size is 101. And then when we call this coin flip 1000, 1000, 100 times. If you still remember, this function is flipping the coin 1000 times and get the probability of heads and return the probability heads right here. So for this function, each of the elements in X is the result for one experiment for using this function. Okay, and let's run it. Cool. So yeah, we get a result like this, right? So what this means, so first thing, if you look at the plot, it's very the shape is kind of bad, right? This is, I would say, this is not a very good picture or bar plot, but there are two trends we can see. So one thing is most of the cases are around here, right? That means most of the probability calculated are around 0.48 to 53 or 5 something. So that's one thing. Another thing is because here we only do this trial because this takes some time, so I only tried 100 times. But you guys can try more times and see how it works. But basically, the trend is if you have more time, this shape will be better, and also you can see a better trend of like most of the elements falling into a very small range, right? And all of this, like the numbers, when we add them together, it should be 100. But anyway, the probability is all falls into this range, right? Which makes sense. But there is small probability to like there is a small chance to make some like bias or 0.5, and the further the chance is lower or smaller. Okay, cool. So I think I hope you guys understand this flip coin experiments. So let's move on to next example called Monty Hall game. Monty Hall. So first, let me ask: do you do you know this game, Monty Hall game? If you know, press a 1. If you don't, type a 2. Yeah, I think the experiment or the examples today is kind of interesting. Okay, I saw someone doesn't know. So let's Google what is this. Google what is Monty Hall game or Monty Hall problem. So let's look at this. Let's look at this figure here. So in search of a new car, the player picks a door. So in total, we have 3 doors here. And the game, so first the player picks one door. So here for this example, the player picks door 1, and the game host then opens one of the other door. So for this example, it's 3, to reveal a goat. And then give the offer to let the player to switch door to 1 to 2. So that means so our goal is to find the car, of course, right? Because goat is bad, and we wanna so the first so the player first randomly choose one door, and then because we have two goats and one car only after the door. So no matter what you choose, what the player choose, the host can always find a door that has a goat, right? So the host opened the one of the other door with a goat, and then the player can choose to switch or not. By switch, I mean you can switch the other one, switch to the other one. So for this example, is 2, or you can stick to the 1. I hope you guys understand the questions now. Okay, cool. So yeah, this question, here we have a function for it to simulate this kind of games. So let me give you guys, I think this is kind of complicated. So let me give you guys 5 minutes to understand this code. Yep. Okay, so yeah, if you have questions or you want to discuss with us, you can unmute yourself. And I will give you guys 5 minutes to read through this. So first, you can skip the plotting part. And just focus on the uncommented parts. So anyone wants to talk about this? Okay, so yeah, let me first let's go through this together. So for this Monty Hall tie, we first we create a variable to store the number of successful switch door wins. What does that mean? That means because the player have the choice to switch or not, right? So this record like when the player choose to switch, what's the probable if he wins or find the car, then we count that as a we just count the events of that happening in this variable. Because this we are still doing Monte Carlo simulation, so we have to define number of trials, number of simulations. So here we use 10,000. And first we have an available set. So this set is like, because we have 3 doors in total, right? So we name the door to be 1, 2, and 3. And first we choose one of them. So this choice is like we randomly get a number from 1, 2, and 3, right? And then available is we subtract the or we delete the choice from the available because you already choose it, right? So that's not available now. Let's say if the available is 1, 2, 3 and the choice is 3, then available is 1, 2, right? And for car we also have to predefine where the car is, right? So we define that here. And then Monty, which is the host opens the door with gold. So this part, it just make sure. So this while loop just make sure Monty opens the right door, opens a door with a gold. Okay. So then available is because Monty had a choice and the player also made a choice. Then available is actually now contains only one element, right? So if the players choose to switch, that means the player choose the only available one, right? And then if the choice is correct, which means the choice is equals to the car, right? Then that means this switch wins. So we add 1 to this counting number here, right? And then we display the probability of blah 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 blah, and that's wrong. Let me run this code. Yep. So we got this probability, right? And we can, so in this way, we find the probability of winning by staying with the first choice is this, and the probability of winning by switching is this. So let me uncomment this thing. So this plot can help us better understand what this is doing, I guess. Yeah. So this is the it's similar. So this is switch, and this is stay, and this means win, right? So actually, we can look at this pie plot, and we are doing this for every trial. So as you can see the trend, like how this winning by switch or winning by stay changes. Okay, yeah. So I think yeah, that's it for today. I hope you guys enjoy those examples.